let's start talking about mathematical induction now. So we're going to build our machine that allows us to prove some results. And let me talk about what this machine is. So first of all, I just want to say that I'm going to call P of n an open sentence. So think of that as our open sentence. So here's the idea. If we know that open sentence is true for some least element m, we're thinking of m here as our least element, and we have this implication, which is if this open sentence is true for k, then it's also true for k plus 1. If we know that that is true for all k that are greater than or equal to our least element, then we get that the statement is true for all numbers that are greater than or equal to our least element, m. Let me draw a bit of a diagram to show you what's kind of going on. So we have this machine. So this machine, this is kind of our step 2 here. This machine allows us, if we put in something that we know is true, if we put in pk, if we know the statement is true for some value k, the machine turns it into the statement being true for the next number up, pk plus 1. And the idea is, well, if we have it for k, then we have it for k plus 1, and we can just take that and put that back into the machine. And if we put in pk plus 1, then the machine gives you the truth of the next statement, pk plus 2. And then you can take that, put that back into our machine turns that into the truth of the next statement, the next number pk plus 3, and so on. So you can think, once we have it for 1, this machine allows us to get the truth value for all other statements. The only thing is, we need something to start our machine going, and that's our base step. We're thinking of our base step as kind of like the fuel for our machine. So here, think the fuel for our machine. And the inductive step, that's our machine. Think machine. So let's do an example. And this is kind of one of the simplest examples we can do. And it's show that the sum of all the numbers from 1 to n is n times n plus 1 all over 2. And just a reminder for notation, this means take whatever this is and run it through all the numbers from I equals 1 up to n and add them together. So this is 1, and then go up to the next one, 2, and then go up to the next one, 3. Keep going until you get to n. So that's what this whole notation here means. And we want to show that that is n times n plus 1 all over 2. Okay, so all inductions basically work the same way. We show our base step, so that's for the smallest possible value, our least element, and in this case it's when I equals 1. And then once we show it's true for the base step, well, then we can do our induction machine here. So we're going to assume the if part is true and show that the then part is true. Okay, so let's go ahead. So this is by induction. Let me make a little more room here. Let's do our base step first. So that is when n equals 1. So we need the sum from I equals 1 to 1. Well, that's pretty easy, of I. Does that equal 1 times 1 plus 1 over 2. And just to be clear, our n is 1, so that's where our n's are here. So we're just checking if this is true for our least element. And, well, the sum of all the numbers from 1 to 1, that's just 1. That's pretty easy. And here we have 1 times 1 plus 1 is 2 over 2, which is 2 over 2, which is, of course, 1. So these indeed equal. We're pretty happy with that. So our base step is true. Let's do our inductive step now. So that was our base step. Inductive step. So what we're going to assume is we're going to assume that this is true for some value k, for some k in our index set. And our index set in this case is the natural numbers because we're starting at 1. Okay, so let's assume that, let's say for some natural number k, that the sum from I equals 1 to k of I, we're going to assume that that equals k times k plus 1 over 2. So we're saying if it's true for some number k, we need to show that it's true for the next number, k plus 1. So to show, we want to show that the sum from I equals 1 to the next number up, k plus 1, equals k plus 1 times k plus 1 plus 1, so k plus 2, over 2. So instead of k, we're just putting k plus 1. So that's what's going on there. Just to make a little bit of room, I'm going to erase our base step here, but hopefully you guys have that in your notes already. So let's go ahead and do this. So let's consider the sum from I equals 1 to k plus 1 of I. And remember, well, what does that equal? That equals 1 plus 2 plus 3 plus 4 plus 5, all the way to plus k, then plus k plus 1. So I'm going to write it out once kind of in its long form. So 1 plus 2 all the way to plus k, then plus k plus 1. And if you like, I can think of it bracketed like that. And this is where we're using our we call this the inductive hypothesis. Let me give this a name here. What we're assuming we call the inductive hypothesis. Okay. So, remember, we're assuming that this is true for k. So we have the sum from I equals 1 to k of I plus k plus 1. This is just writing this in our summation notation. And we know what this is, in fact. We know this, by our inductive hypothesis, is k times k plus 1 over 2. Because remember, we assumed that this was true. So we know our sum there equals k times k plus 1 over 2 plus k plus 1. So here's where we're using our inductive hypothesis to get from here to here. And it's a good idea to tell people that you're using that by inductive hypothesis. Okay. And we keep going. Now we just have to do a little bit of algebra to show that it's of the form k plus 1 times k plus 1 plus 1, which is k plus 2 over 2. Okay, get a common denominator here. So we get, in fact, let's multiply things out. So we get k squared plus k over 2 plus, and I'm going to multiply top and bottom of this guy by 2 and expand out, which is 2k plus 2 over 2, which is indeed k squared plus 3k plus 2 over 2, and that can be factored into k plus 1 times k plus 2 over 2. So we've done it. We started assuming that the sum from 1 to some number k is k times k plus 1 over 2. And we showed that it must be true that it's true for k plus 1 as well, for the next number up. So therefore, we've proved the result. Thus, the result is true for all natural numbers. And we're done. We showed it's true for 1. That was the gasoline in our step. Remember that base step that we did first. Since we built our machine here, we can take the truth for one value and turn it into the truth for the next value up. So we put 1 into our machine, and we get the truth of 2. Now we know it's true for 2, so we put 2 into our machine, and we get the truth for 3. And we keep going as far as we want, infinitely far, and that's how induction works. So again, the steps: first you do your base step, then you do your inductive step. Let's do one more example, and then I'll get you guys to do one. So let's show that the sum of these odd numbers from 1 all the way up is n squared. And let me be clear about this. Let's say for all n in the natural numbers. So this is saying that the sum of the first n odd numbers is n squared. And if I wanted to write this in summation notation, you can try this as well. Make sure you understand this, but it is the sum from 1 to n of 2i minus 1. That equals n squared. That's what we want to show. So our index set is the natural numbers, which has a least element of 1. So let's prove this by induction. Let's do our base case first. We always do our base case first. All right. The sum from I equals 1 to 1 of 2i minus 1, does that equal 1 squared? So this is when n equals 1. Of course, our least element of our set. So, well, this is just 2 times 1 minus 1. Does that equal 1 squared is 1? And 2 times 1 minus 1 is 1. 1 does equal 1. We like that. So our base case is true. Let's do our inductive step now. Let's assume our inductive hypothesis now. So we're going to assume that, I'll write it in summation notation here. The sum from, in fact, maybe I'll write it here first. So for sum k in our set, and our set is the natural numbers this time. Just to be clear, we need a different variable here because we're actually picking a number here, k, and we're showing that it's true for the next value, k plus 1. So we need this extra variable k. We can't use n. So here, don't use n from theorem. And if the theorem uses a different variable that isn't n, don't use that variable. It's just key that you don't use the variable given to you in the theorem. You need something different because you're picking a value k. So assume for some k that the sum from I equals 1 to that number k of the odd numbers equals k squared. So the sum of the first k odd numbers is k squared. And I'm going to write this to show here, just to make sure we understand what we're showing. So we're showing that the sum of the first k plus 1 odd numbers, and I like to put brackets around what the sum is taking, just so it's very clear that it's the sum of 2i minus 1. It's not the sum of 2i and then subtract 1. It's the sum of 2i minus 1. We want to show that that equals k plus 1 squared. Okay, so let's consider the sum from I equals 1 to k plus 1 of 2i minus 1. Remember, we're always looking for a way to use our inductive hypothesis. That the sum, in this case, the sum from 1 to k of 2i minus 1 equals k squared. We're always looking for a chance to use that. So maybe I'll make a little note here. Look for a way to use the inductive hypothesis. So here, well, instead of just taking the first k plus 1 numbers, I can take the first k and just have the last one on its own. So this is the same as the sum of the first k odd numbers plus that last one that didn't get included, 2 times k plus 1 minus 1. So just to be clear here, I'll put this in brackets, why not? Just to be clear, these k plus 1 odd numbers, these are the first k of them from 1 to k, and the last one, the k plus 1th one, is this guy. Okay. So now that we have that, let's scroll down to give myself a little more room, and I'll probably just start over here again, actually. It's getting a little messy. I apologize for that. Maybe I'll draw a little arrow just to remind you guys where we're going here. There we are. So let's use our inductive hypothesis. So this equals k squared, and then we have plus 2 times k plus 1 minus 1 by our inductive hypothesis. And let's expand things out, so we get k squared plus 2k plus 2 minus 1, which is k squared plus 2k plus 1. And of course that factors into k plus 1 all squared, which is what we wanted to show. We started with, in this case, the left-hand side. We used our inductive hypothesis. That's important. You always need to use your inductive hypothesis, because otherwise there's kind of nothing to show. If you're not using the inductive hypothesis to prove a result, well, you don't need that hypothesis then. But in all the problems that we'll get, we'll definitely use our inductive hypothesis. So we find a way to use that, and we notice, well, we can just split off that last guy out of the k plus 1 odd numbers. We'll take the first k. We'll use our inductive hypothesis, which says that that equals k squared. And we have this 2 times k plus 1 minus 1 term left over. Little bit of algebra gets us to where we are. And we can say, by induction, the result is proved. And we're done. Now, a couple of notes I want to talk about. First of all, what's really cool is we did prove some results. And that's a nice thing about proving results. I didn't want to do that. Let me scroll everything up. There we are. So let me show both of these here. What's really cool is that we proved this. This is actually a proof here. Whenever we have the sum of the first n numbers, whatever they are, from 1 to n, we can use the formula n times n plus 1 over 2 instead. So we can replace the sum of the first n numbers from 1 to n by n times n plus 1 over 2. They equal. We just showed that. Here, whenever we're adding up the first n odd numbers, we can replace that by n squared. So that's fantastic. The second thing I want to talk about is, well, what's going on here in general? Let me go down to the second one, since I have a little more room. Most of these induction problems, especially the ones that we first use when we're learning, are all of the same form. So we always do our base case. We do our base case, we show it's true for the least element of our set. Then we do our inductive step. And if you think about it, the inductive step, basically most of it is just follow your nose. So we write down what we're assuming, we write down what we want to show, and then usually we start with one side and we want to get to the other. And the only bit where we have to do a little bit of creative thinking is thinking of a way to use our inductive hypothesis. So once we figure that out, we use our inductive hypothesis. So this is it down here. This is our inductive hypothesis. We used it. Once you use your inductive hypothesis, it should just be a matter of doing a little bit of algebra to complete the argument. Or maybe a little bit, if you're not doing things with the numbers, maybe you're doing things with sets or logic or something like that, well, maybe you'll have to do a little bit of logic arithmetic or set arithmetic, whatever. But my point is, once you use that inductive hypothesis, it should just be a matter of cleaning everything up in order to get the result that you're looking for. So in some sense, there's not a lot of thinking or creativity to this. The base case you just do, the inductive step you set up the same way. Once you figure out how to use your inductive hypothesis, then do the algebra to show what you want at the end. And that's it. Let's look at another example. Let's try this one. So we want to show that the sum of the first n squares from I equals 1 to n is this formula, n times n plus 1 times 2n plus 1 over 6. My suggestion to you guys is to pause the video right now and try this yourself. It goes in the same form as all of the other ones, so you can use those as a guide for yourself and see if you can understand what's going on. Remember, the base case is you just do it for the smallest element. In this case, it's when n equals 1, since we're starting at 1. For the inductive step, you're just assuming it's true for some value k, showing that you need to prove it for k plus 1, and then figuring out how to use your inductive hypothesis to simplify things. And in this case, it'll be pretty easy because it'll be very similar to the ones we did in the previous two examples. Then do your algebra to get the formula that you're looking for. Okay, so now that we're back, let's go ahead and do this. So let's do our base step, our base case. Remember, this is the gasoline that allows our machine to work. We need to know it's true for one value so we can initially put that into our machine to get the next one, and then the machine can just keep running off of the values that it produces. Okay, so that is when n equals 1. So we want to show that the sum from I equals 1 to 1 of I squared, does that equal 1 times 1 plus 1 times 2 times 1 plus 1 over 6. So this is just 1 squared. Does that equal 1 times 2 times 2 times 1 plus 1 is 3 over 6. And this is, of course, 6 over 6. So 1 does indeed equal 1. Our base case seems true. In fact, not even seems true, is true. Let's do our inductive case now. All right, so let's assume that it's true for some k in our index set. Our index set in this case is the natural numbers. We're starting at 1. That the sum of the first k squares, I'm going to assume that that is equal to k times k plus 1 times 2k plus 1 over 6. And we want to show, and again, just know that I like to write this to show because we're just learning some new proof techniques, but out in the mathematical wild, when you're reading papers or reading the book, they might not say what they're going to show, they will just show it. But we want to show that the first k plus 1 squares added together is k plus 1 times k plus 1 plus 1, so k plus 2, times 2k plus 1 plus 1, or 2k plus 3, over 6. So let's go ahead and do this. And remember, really, we just need to figure out a way to use our inductive hypothesis, and the rest should be following your nose. So consider the first k plus 1 squares. Well, that's the same thing as the first k squares plus that k plus 1th square. Because remember, this is 1 squared plus 2 squared plus 3 squared, all the way to plus k squared plus k plus 1 squared. Well, all the way up to k squared is this term, and then you just have that last term, k plus 1 squared. Now, here is our chance to use our inductive hypothesis. We're assuming that this equals k times k plus 1 times 2k plus 1 over 6. So, this equals k times k plus 1 times 2k plus 1 over 6 plus k plus 1 squared. And that's by our inductive hypothesis. Okay, so now that we use that, it's all a matter of doing the correct algebra to get this in the form that we want. And I'll just write down here that this is 2k plus 3. Okay, so if you haven't tried it yet, I think it's a good idea to pause the video now and practice your algebraic skills. Make sure that you can turn this expression here into k plus 1 times k plus 2 times 2k plus 3 over 6. If you can do that, you're doing well. Okay, now that we're back, let me give myself a little more room. I'm going to go all the way over here. So here are my thoughts. First of all, I'm adding 2 terms. I want to end up with the denominator of 6. So I might as well have them over a common denominator, multiply top and bottom by 6 here. The second thing that I realize is that I need a factor k plus 1, and I already have a factor of k plus 1 in both terms. So maybe I'll factor that out right away. So this is the same thing as k plus 1 times k times 2k plus 1 over 6 from the first term, plus I took out one of the k plus 1s from the second term. So this is 6 times k plus 1 over 6 from the second term. And let me scroll down to make a little more room. So this equals, we have our k plus 1 on the outside, which will multiply back when it comes time to, but let's simplify what's going on here. So let's expand this. I'd say that would be the easiest way. So this is 2k squared plus k over 6. Maybe I'll do it all in one. So that is the first bit here. And then let's expand out the next bit, plus 6k plus 6. That is that bit there. Okay. So this becomes k plus 1 times 2k squared plus 7k plus 6 over 6. And we know what we're supposed to get, but just as a bit of factoring practice, we want to split this 7k, or this 7, into two numbers that multiply together to give you 2 times 6, which is 12. So they add to give you 7, and multiply to give you 2 times 6, which is 12, and 4 and 3 does it. So let's do this the long way, just to get some factoring practice. So I'm going to split up that 7k into 4k plus 3k plus 6 over 6. And let's group them like this. If you group them the other way, 3k plus 4k, you'd still get the same answer. Doesn't really matter. So this is k plus 1. And now let's factor out what's in common from both of these. We have, in the first bracket, we have a 2k as a common factor. And we're left with a k plus 2. And in the second bracket, we have a common factor of 3. So let's factor out 3, and we're left with k plus 2. And this is all over 6. And we know we did it correctly because, hey, look, we have a common factor here, k plus 2. So we can separate that. Let me go ahead and do this. So it's k plus 1 times k plus 2. That's that common factor. We're left with a 2k from the first term, a 3 from the second term, over 6. And then, hey, if you're thinking about it, well, this is just k plus 1 over 1. So we can multiply these fractions, and we get exactly what we want. K plus 1 times k plus 2 times 2k plus 3 over 6. And just as a reminder, let me scroll up. That's what we wanted to show. K plus 1, k plus 2, 2k plus 3 over 6. Scroll back down. So by induction, the result is proved. And we're done. Okay, so that's it for this video. In the next video, we'll do 3 more induction problems so you can get some more practice doing this stuff. It's a mathematical technique that's not particularly difficult once you get the knack of it. And the way to get the knack of it is to just keep practicing. So we'll do a bunch more examples in the next video. And like I say in all my videos, it's a really good idea to pause the video before we do the answer to a problem. You should try it yourself and see how well you do. And even if you get stuck partway through, you can go as far as you think you can, and then watch it up until that point. See if if it matches up with what you have, and then watch a bit to get over the hump, and then pause the video again and see if you can finish off the problem. So that's always a good suggestion.